And now in this lecture we'll find out the radius of a circle using two different methods. In the drawing we have triangle ABC that blocks this circle, or this circle is inscribed by triangle ABC. In addition, we know that this is angle ABC that is equals to 60 degrees, and this angle ACB equals to 75 degrees in its size, and side BC of this triangle ABC equals to 2 units in its length. Again, our mission is to find out the radius R of this circle. So we'll start with the first method, and we'll do a construction, that is to say from point C, we'll draw perpendicular on side AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB as D. By doing this construction, we created here the right triangle DBC. So I copy the right triangle DBC. In a new page, we analyze this right triangle DBC. So actually, this is the right triangle DBC that I copied from the original drawing. Angle DBC equals to 60 degrees, and side BC equals to 2 units according to what is given as the question. On this right triangle DBC, cosine 60 degrees equals to dB over BC. So it is dB over BC, and BC is 2. So cosine 60 degrees equals to dB over 2. Cosine 60 degrees is 1/2. So we substitute cosine 60 degrees by 1/2, and we'll get that 1/2 equals to dB over 2. Here we'll multiply this equation by 2, and finally we get that dB equals to 1 unit in its length. dB equals to 1. So actually, this line segment dB equals to 1 unit in its length. We'll continue to focus on this right triangle DBC. On the right triangle DBC, sinus 60 degrees equals to DC over BC. Sinus 60 degrees is equal to 3 over 2, and it is equals to DC over BC, and BC is 2. So we substitute BC by 2. So in conclusion, we found out that square root of 3 over 2 equals to DC over 2. We will multiply this equation by 2, and finally we get that DC equals to the square root of 3 units in its length. So here, DC equals to the square root of 3 units in its length. We continue to focus on the right triangle DBC. The sum of the angles in any triangle is equal to 180 degrees, and especially it is true in the right triangle DBC. So which angles we have in the right triangle DBC? We have this angle that is 90 degrees plus this angle that is 60 degrees. 90 degrees plus 60 degrees, it is 150 degrees. So the missing angle must be equal to 30 degrees. In order to complete the sum of the angles on this right triangle DBC to 180 degrees, the missing angle here must be equal to 30 degrees. Okay, so it is given us the question that the big angle ACB, this is the big angle ACB, that is equals to 75 degrees in its size, and the small angle BCD equals to 30 degrees. So the big angle minus the small angle will be equal to the missing angle, that is actually angle DCA. Again, the big angle minus the small angle equals to the missing angle DCA. The big angle equals to 75 degrees, the small angle equals to 30 degrees. 75 degrees minus 30 degrees, it is 45 degrees. So we actually found out that the missing angle DCA equals to 45 degrees in its size. In the next step, I will copy the right triangle DCA in a new page, and we will analyze this right triangle DCA. So actually, this is the right triangle DCA that I copied from the original drawing. We just right now found out that this angle DCA equals to 45 degrees, and we already found out that side DC equals to the square root of 3 units. We know that the sum of the angles in this right triangle DCA must be equal to 180 degrees. So, which angles we have in this right triangle DCA? This angle equals to 90 degrees, plus this angle that is equal to 45 degrees, 90 degrees plus 45 degrees, it is 135 degrees. Therefore, the missing angle here must be equal to 45 degrees in its size. In order to complete the sum of the angles in this right triangle DCA to 180 degrees, the missing angle here must be equal to 45 degrees. So those two angles, they are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, they are equal size. So those two sides that are located in front of those two equal angles must be also equal to each other. That is to say, side AD must be equal to side DC. AD equals to DC. But we already found out that DC equals to the square root of 3 units in its length, so we can write here that DC equals to the square root of 3 units. And from this equation, AD equals to DC equals to the square root of 3 units, we will derive that side AD also equals to the square root of 3 units in its length. Side AD equals to the square root of 3 units in its length. Here also, this is line segment AD that is equals to the square root of 3 units in its length. We will continue to focus on this right triangle ADC. We will implement the Pythagoras theorem on this right triangle ADC. Here by PT is the abbreviation for Pythagoras theorem. In this right triangle ADC, according to the Pythagoras theorem, AC squared equals to AD squared plus DC squared. So AC square, that is the square of the hypotenuse, equals to AD square. AD is square root of 3, therefore AD square is square root of 3 square, that is 3, plus DC square. This is also square root of 3, therefore DC square is square root of 3 square, that is 3. So AC square in total equals to 3 plus 3, that is 6. AC square equals to 6. Here we'll take a root out of this equation, and finally we get that AC equals to the square root of 6 units in its length. So side AC of triangle ABC equals to the square root of 6 units in its length. In the next step, I will present to you a new rule, and we'll implement the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is described by a triangle ABC that could be any triangle, the radius R equals to the area of triangle ABC that blocks the circle over S. S is the semi-perimeter of the same triangle ABC, and the semi-perimeter of any triangle equals to the perimeter over 2. So the drawing of this rule number 15, is this. So in the drawing we have a circle that is described by triangle ABC. So the radius R of this circle will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. We can actually implement rule number 15 in our drawing. Whenever we have a circle that is described by a triangle, we can implement rule number 15. For that reason, we can implement rule number 15 in our drawing also. So according to rule number 15, the radius R of this circle that is described by triangle ABC will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. I repeat again. The radius R of our circle that is described by triangle ABC will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter S of the same triangle ABC. So the area of triangle ABC, the area of any triangle equals to the base of the triangle times the height to the base over 2. And we have to divide it by S, that is the semi-perimeter of the same triangle ABC. We choose the base of this triangle ABC as AB. So the base is AB. The height to the base must create 90 degrees with the base, so the height is CD, because CD creates 90 degrees with the base AD. So the height is CD divided by 2. And we have to divide it by S, that is the semi-perimeter of triangle ABC. AB is square root of 3 plus 1. So we substitute AB by square root of 3 plus 1 times CD. CD equals to the square root of 3 units. So we substitute CD by square root of 3 divided by 2, and we have to divide it by S. S is the semi-perimeter of triangle ABC, and the semi-perimeter of this triangle ABC is the perimeter over 2. The perimeter of this triangle ABC equals to AB plus AC plus BC. AB plus AC plus BC, and when we divide the perimeter by 2, we get the semi-perimeter S. So the radius R equals to the square root of 3 plus 1 times square root of 3 divided by 2, and we have to divide it by AB. AB is equal to 3 plus 1 plus AC. AC equals to the square root of 6 units in its length. So we substitute AC by square root of 6 plus BC. Okay, BC equals to 2 units in its length according to what is given as the equation. So we'll substitute BC by 2 or divided by 2. So the radius R of this circle equals to the division of those two expressions with each other. The value of this expression, it is equals to 2.366. That is to say the area of triangle ABC is 2.366 square units divided by S. S is this expression, and the value of this expression in total, it is equals to 3.591, and 2.366 over 3.591 equals to 0.6589. In conclusion, found out that the radius R that we are looking for, the radius R of this circle, equals to 0.6589 units. Okay, so we finished with the first method. In the next step, I present to you how to find out the radius R of this circle according to the second method. So in the second method, we will define the center of this circle. Here, this point is O. We will define the point of tendency of tangent BC with this circle as D. We will define the point of tendency of tangent AC with this circle as F. And we will define the point of tendency of tangent AB with this circle as E. Here, point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle. That is equal to R according to our definition. You can implement here rule number 1. I repeat quickly on rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have tangent AB, that is tangent to this circle point M. Point M is the point of tendency. And we have the radius OM that is drawn to point M. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule number 1. We can actually implement rule number 1 in our drawing. Why? Because in our drawing, we have the radius OD that is drawn to point D. That is to say, it is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Likewise, we join points O and D together by a straight line. 9 segment OE is the radius of this circle that is equal to R. So here we have the radius OE that is known to point E, and therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and F together by a straight line. Line segment OF is the radius of this circle that is equal to R. Again, here we have the radius OF that is known to point F, that is the point of tendency of tangent AC with this circle. Remember, we have a radius that is known to the point of tendency. Then tangent AC will be perpendicular to the radius FO. If AC is perpendicular to FO, then this angle equals to 90 degrees. And this angle also equals to 90 degrees, according to the same rule, rule number 1. We can implement in this drawing, in our drawing, also rule number 2. I'll take quickly on rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. In the drawing we have a circle, and we have the common standpoint point P. From the common standpoint point P, we have two tangents to this circle, tangent BA and tangent BB. According to this rule number 2, they are equal to each other. That is to say, PA equals to PB. We can actually implement rule number 2 in our drawing. One, because in our drawing, we have, if we focus on the common standpoint point C, from the common standpoint point C, from the common standpoint point C, we have two tangents to this circle, tangent CD and tangent CF. And according to rule number 2, they are equal to each other. That is to say, CD equals to CF. So I can write here that CD equals to CF according to rule number 2. Likewise, we focus on the common standpoint point B. From the common standpoint point B, we have two tangents to this circle, tangent BD and tangent BE. And according to rule number 2, they are equal to each other. That is to say, BD equals to BE. So I write it down. Tangent BD equals to tangent BE according to the same rule number 2. In the next step, we join points O and C together by a straight line. And we join points O and B together by a straight line. And we will prove that those two right triangles can run to each other. That is to say, we will prove that the right green triangle, triangle ODB, is congruent to the right yellow triangle, triangle OB. So I write it down. We'll prove that the right green triangle BOD is congruent to the right yellow triangle OBE. So why the yellow triangle is congruent to the green triangle? First of all, side EO of the yellow triangle equals to side OD of the green triangle. They are both the radii of the circle, therefore they are equal to each other. I repeat again, side EO of the yellow triangle equals to side OD of the green triangle. They are both equal to R because they are both the radii of the circle, therefore they are equal to each other. In addition, BE equals to BD according to rule number 2. Here, BE equals to BD according to rule number 2. Repeat again, side BE of the yellow triangle equals to side BD of the green triangle according to rule number 2. And finally, side BO is a common side that belongs to both triangles. So I can write down that BO equals to itself. It's a common side that belongs to both triangles. Repeat again, BO equals to BO, it's a common side that belongs to both triangles. So I actually prove that all the three sides of the yellow triangle BEO are correspondingly equal to all the three sides of the green triangle BOD. Therefore, we actually proved that those two right triangles can go into each other according to side rule. So I write it down. I actually proved that the yellow triangle BEO congruent, this is the sign of congruent, to the green triangle OBE, and they congruent to each other according to side rule. And from the fact that those two triangles congruent to each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go to each other, therefore the two corresponding angles, those two corresponding angles must be also equal to each other. So this is angle EBO in the yellow triangle. And it is equal to this angle, this is actually angle OBD in the green triangle. This again, angle EBO equals to angle OBD. So if we define one of those two angles as theta, then the other angle must be also equal to theta because they are equal to each other. So here we have theta plus theta, they must be equal to 60 degrees. That is to say 2 theta equals to 60 degrees. Here we divide this equation by 2 and we get that angle theta equals to 60 degrees over 2 is 30 degrees. So actually this is angle theta that is equal to 30 degrees in its size. So I write it now. In the next step, I will copy the right triangle OBD in a new page and we will analyze this right green triangle, triangle OBD. So actually, this is the green right triangle OBD that I copied from the original drawing. This is the angle theta that is equal to 30 degrees in its size, and side OD equals to R, is the radius of the circle. So in this right triangle OBD, tan means 30 degrees equals to OD over BD. So tan is 30 degrees equals to OD. OD is R, so we substitute OD by R, so it will be R over BD. So tan 30 degrees equals to R over BD. Here we multiply this equation by BD, and we get that BD times tan 30 degrees equals to 1. Here we will divide this equation by tan 30 degrees, and we get that BD equals to R over tan 30 degrees. So here, this line segment BD equals to R over tan 30 degrees in its length. So we write it down. In the next step, we repeat on the same process on those two right angles. That is to say, we prove that the orange right triangle ODC is congruent to the pink right triangle OFC. So why those two right triangles can go into each other? First of all, OF equals to OD. They are both the radii of the circle, therefore they are equal to each other. In addition, CF equals to CD according to rule number 2. Here, CF equals to CD according to rule number 2. And finally, CO is a common side that belongs to both triangles. So we can write down that CO equals to itself is a common side that belongs to both triangles. So actually proved that all the three sides of the pink right triangle OFC are correspondingly equal to all the three sides of the orange right triangle ODC. Therefore, we proved that those two right triangles can go into each other according to side rule. And from the fact that those two right angles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent angles are equal to each other. So this is angle FCO. And it equals to this angle is actually angle OCD. So if we define one of those two angles as alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 75 degrees. That is to say 2 alpha equals to 75 degrees. 2 alpha equals to 75 degrees. We divide this equation by 2 and finally we get that alpha equals to 75 degrees over 2, that is 37.5 degrees. So this is angle alpha, that is equal to 37.5 degrees in its size. In the next step, I'll copy the orange right triangle ODC in a new page and we'll analyze it. So actually, this is the right orange triangle that I copied from the original drawing. This is angle alpha that is equal to 37.5 degrees in size, and side OD equals to R, it is the radius of the circle. In this right triangle ODC, tangents 37.5 degrees equals to OD over DC. OD is R, so it is R over DC. So tangents 37.5 degrees equals to R over DC. Here we multiply this equation by DC and we get that DC times tangents 37.5 degrees equals to R. Here we will divide this equation by tangents 37.5 degrees and finally we'll get that DC equals to R over tangents 37.5 degrees. So this line segment DC equals to R over tangents 37.5 degrees. So I write it down. From the drawing, it is very easy to see that BC equals to BD plus DC. Again, BC equals to BD plus DC. So I write it down. Repeat again. BC equals to BD plus DC. BC equals to 2 according to what is given as the question, so we substitute BC by 2 and it is equals to BD. BD is minus 30 degrees, so substitute BD by minus 30 degrees. By BD equals to R over minus 30 degrees, therefore we substitute BD by R over minus 30 degrees. Plus DC. DC is R over minus 37.5 degrees, so we substitute DC by R over minus 37.5 degrees. In conclusion, we found out that 2 equals to R over minus 30 degrees plus R over minus 37.5 degrees. So 2 equals to here we take out R as a common factor from those two expressions. So what is left from R over minus 30 degrees after we took from it R as a common factor? What is left is actually 1 over minus 30 degrees plus what is left from R over minus 40 degrees. What is left from R over minus 37.5 degrees after we took from it R as a common factor? What is left is actually 1 over minus 37.5 degrees. In conclusion, we found out that 2 equals to R times 1 over minus 30 degrees plus 1 over minus 37.5 degrees. So 2 equals to R, and we have inside the brackets 1 over minus 30 degrees. That is actually 1.732 plus 1 over minus 37.5 degrees. That is actually 1.3032. In conclusion, we found out that 2 equals to R times 1.732 plus 1.3032. So 2 equals to R, and 1.732 plus 1.3032 equals to 3.0352. Here we divide this equation by 3.0352, and finally we get that R, the radius that we are looking for, the radius of the circle, this is described by triangle ABC, equals to 2 over 3.0352. And 2 over 3.0352 equals to 0.6589 units. So the radius of the circle, according to the second method also, is equals to 0.6589 units. So actually, in both methods, we found out that the radius R of this circle equals to 0.6589 units. In the next step, I will summarize the lecture. We start with the first method also. In this lecture, we found out the radius R of this circle that is described by triangle ABC. In the drawing, we have a circle that is described by triangle ABC, or triangle ABC blocks this circle. This angle ABC equals to 60 degrees. This is angle ACB, this is equals to 75 degrees in size. And we also know that side BC of this triangle ABC equals to 2 units in its length. Again, our mission is to find out the radius R of this circle. So in the first method, we did the construction. that is to say, from point C we draw perpendicular on side AB. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB is D. By doing this construction, we render the right triangle CDB. So I copy the right triangle CDB in the new page and we analyze this right triangle CDB. This is the right triangle CDB that I copied from the original drawing. In the right triangle CDB, cosine 60 degrees equals to dB over BC. So it is dB over BC, and BC is 2, so it is dB over 2. So cosine 60 degrees equals to dB over 2. Cosine 60 degrees is 1/2, so 1/2 equals to dB over 2. We multiply this equation by 2 and finally found out that dB equals to 1 unit in its length. Here, this line segment dB equals to 1 unit in its length. We continue to focus on this right triangle DBC. In this right triangle DBC, sine of 60 degrees equals to DC over BC. Sine of 60 degrees equals to DC over BC. Sine of 60 degrees is square root of 3 over 2. That is equals to DC over BC. BC is 2. So, in conclusion, found out that square root of 3 over 2 equals to DC over 2. We multiply this equation by 2 and finally found out that DC equals to the square root of 3 units in its length. Here, DC equals to the square root of 3 units in its length. We continue to focus on this right triangle DBC. On this right triangle DBC, the sum of the angles must be equal to 180 degrees. So which angles we have inside this right triangle DBC? We have this angle that is equal to 90 degrees plus this angle that is equal to 60 degrees. 90 degrees plus 60 degrees equals to 150 degrees. So the missing angle must be equal to 30 degrees. So the big angle ACB equals to 75 degrees in its size. This is the big angle. The small angle equals to 30 degrees. So the big angle minus the small angle equals to the missing angle, that is actually angle ACD. That is to say, the big angle is 75 degrees minus the small angle that is 30 degrees. 75 degrees minus 30 degrees equals to the missing angle that is 45 degrees. So the missing angle ACD equals to 45 degrees in its size. Then I copy the right triangle ACD in a new page and we analyze this right triangle ACD. This is the right triangle ACD that I copied from the original drawing. The missing angle that we found is equals to 45 degrees in its size. And we already found out that this equals to the square root of 3 units in its length. In this right triangle ADC, the sum of the angles must be equal to 180 degrees. So which angles we have inside the right triangle ADC? We have this angle that is equal to 45 degrees in its size plus this angle that is 90 degrees. 45 degrees plus 90 degrees, it is 135 degrees. Therefore, the missing angle must be equal to 45 degrees. In order to complete the sum of the angles in this right triangle is ADC to 180 degrees, the missing angle must be equal to 45 degrees. So those two angles, they are both equal to 45 degrees, therefore they are equal to each other, and we have the rule that in front of equal angles in the triangle, they are equal sides. So those two sides that are located in front of those two equal angles must be also equal to each other. That is to say, side AD equals to side DC. We have already found out that DC equals to the square root of 3 units in its length, so we can write down here that DC equals to the square root of 3 units. And from this equation, AD equals to DC equals to the square root of 3 units, we derive that AD also equals to the square root of 3 units in its length. So here, AD equals to the square root of 3 units in its length, and we can write down in the original drawing that AD equals to the square root of 3 units in its length. Then we continue to focus on this right triangle ADC. According to the Pythagoras theorem, in this right triangle ADC, AC squared equals to AD squared plus DC squared. So AC squared, that is the square of the hypotenuse, equals to AD squared. AD is square root of 3, therefore AD squared is square root of 3 squared, that is 3. plus DC squared. DC is also square root of 3, therefore DC squared is square root of 3 squared, that is 3. So in total, AC squared equals to 3 plus 3, that is 6. AC squared equals to 6. We took out of this equation and finally found out that AC equals to the square root of 6 units in its length. Here, side AC of this triangle ABC equals to the square root of 6 units in its length. Then I presented to you a new rule, and we implemented the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is described by triangle ABC that could be any triangle, the radius R equals to the area of triangle ABC that blocks the circle over S. S is the semi-perimeter of the same triangle, triangle ABC. The drawing of this rule, rule number 15, is here. We have a circle that is described by triangle ABC. So the radius R of this circle will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter S of the same triangle, triangle ABC. You can actually implement rule number 15 in our drawing. Whenever you have a circle that is described by triangle, you can implement rule number 15. For that reason, you can implement rule number 15 in our drawing. According to rule number 15, the radius R of this circle that is described by triangle ABC will be equal to the area of triangle ABC over the same perimeter of the same triangle, triangle ABC. Repeat again. In our original drawing, according to rule number 15, the radius R of our circle equals to the area of triangle ABC that blocks the circle over the same perimeter S of the same triangle, triangle ABC. The area of any triangle is the base of the triangle times the height to the base over 2 divided by S, that is the semi-perimeter of the same triangle, triangle ABC. We choose the base of this triangle, triangle ABC is AB, and therefore the height to the base is CD. Again, the base is AB, the height to the base is CD divided by 2. All divided by S, that is the semi-perimeter of triangle ABC. AB is equal to 3 plus 1. CD is equal to 3 divided by 2. And the same perimeter of triangle ABC is the perimeter over 2. The perimeter is AB plus AC plus BC, and then if we divide the perimeter by 2, we get the same perimeter S. So R, the radius of the circle, equals to the square root of 3 plus 1 times square root of 3 over 2. Here AB is equal to 3 plus 1, AC is equal to 6, and BC is 2 divided by 2. This expression is the area of triangle ABC, and the value of this expression is 2.366. So the area of triangle ABC equals to 2.366 square units. This expression is the semi-perimeter of triangle ABC, and the semi-perimeter S equals to 3.591. 2.366 over 3.591 equals to 0.6589 units. So found out that the radius R of this circle equals to 0.6589 units. We finished with the first method. In the next step, I presented to you how to find out the radius R of this circle according to the second method. In the second method, we defined the center of this circle here as point O. We define the point of tendency of tangent AB with this circle as C. We define the point of tendency of tangent AC with this circle as F. And finally, we define the point of tendency of tangent BC with this circle as D. Point O, we join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of the circle that we define as R. We have the radius OD that is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees, according to number 1. Likewise, we join points O and D together by a straight line. O is the radius of this circle that is equal to R, The radius OE is drawn to point E, it is the point of tendency of tangent AB with this angle. And whenever a radius that is drawn to the point of tendency, then according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and F together by straight line. OF is the radius of the circle that is equal to R. The radius OF is drawn to point F, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Then we implemented in this drawing rule number 2. If we focus on the common external point C, from the common external point C, we have two tangents to this circle, tangent CF and tangent CD, and according to rule number 2, they are equal to each other. Here, CF equals to CD according to rule number 2. Likewise, we focus on the common external point B. From the common external point B, we have two tangents to this circle, tangent BE and tangent BD, and according to rule number 2, they are equal to each other. That is to say, BE equals to BD according to rule number 2. Then we join points O and C together by straight line, and we joined also points O and B together by straight line. Then we proved that the yellow triangle is congruent to the green triangle according to side rule. So why those two right triangles congruent to each other? I'll repeat quickly on the proof. EO equals to OD, they are both the radii of the circle, therefore they are equal to each other. In addition, EB equals to BE, EB equals to BD according to rule number 2. EB equals to BD according to rule number 2. And finally, side OB is a common side that belongs to both triangles, so we can write down that OB equals to itself is a common side that belongs to both triangles. So actually proved that all the three sides of the yellow triangle EOB are correspondingly equal to all the three sides of the green triangle OBD, therefore those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if one of those two angles is theta, then the other angle must be also equal to theta. So theta plus theta is 2 theta, that is equal to 60 degrees. Here, 2 theta equals to 60 degrees, divided the equation by 2, and finally found out that theta equals to 60 degrees over 2 is 30 degrees. So this is angle theta, that is equal to 30 degrees in its size. Then I copied the right green triangle OBD in a new page, and we analyze this right triangle OBD. This is the right triangle OBD that I copied from the original drawing. In this right triangle OBD, times 30 degrees equals to OD over BD. OD is R, so it is times 30 degrees equals to R over BD. Times 30 degrees equals to R over BD. Here we multiply this equation by BD, and we found out that BD equals to that R equals to BD times 30 degrees. Here we divided this equation by times 30 degrees, and finally found out that BD equals to R over times 30 degrees. Here, this times 7 BD equals to R over times 30 degrees. We repeated on the same process on those two right triangles. We actually proved that those two right triangles can go into each other according to side rule. And repeat quickly on the proof. OF equals to OD. They are both the radii of the circle, therefore they are equal to each other. In addition, CF equals to CD according to rule number 2. Here CF equals to CD according to rule number 2. And finally, CO is a common side that belongs to both triangles, so we can write down that CO equals to itself is a common side that belongs to both triangles. So we actually proved that all the three sides of the right green triangle OFC are correspondingly equal to all the three sides of the right orange triangle OCD. Therefore, those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. So if one of those two angles is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 75 degrees. That is to say 2 alpha equals to 75 degrees. 2 alpha equals to 75 degrees. We divided this equation by 2 and finally found out that alpha equals to 37.5 degrees. So actually, this is angle alpha, this is equal to 37.5 degrees. Then I copy the right orange triangle ODC in the new page, and we analyze this right orange triangle ODC. This is the orange right triangle ODC that I copied from the original drawing. This is angle alpha that is equal to 37.5 degrees. Inside OD equals to R, this is the radius of the circle. In this right triangle ODC, times 37.5 degrees equals to OD over DC. OD is R, so it is times 37.5 degrees equals to R over DC. We multiply this equation by DC and found out that R equals to DC times 37.5 degrees. We divided this equation by times 37.5 degrees and finally found out that DC equals to R over times 37.5 degrees. Let's check again. We found out that this times DC equals to R over times 37.5 degrees. Then from the drawing it is very easy to see that BC equals to BD plus DC. Again, BC equals to BD plus DC. Repeat again. BC equals to BD plus DC. BC is 2 according to what is given as the question. BD equals to R over times 30 degrees. And DC equals to R over times 37.5 degrees. So in total, we found out that 2 equals to R over times 30 degrees plus R over times 37.5 degrees. Here we took R as a second factor from those two expressions, and we found out that 2 equals to R. R was taken out as a second factor, so inside the brackets we left only with 1 over times 30 degrees plus 1 over times 37.5 degrees. So in conclusion, we found out that 2 equals to R times 1 over times 30 degrees plus 1 over times 37.5 degrees. So 2 equals to R, and 1 over times 30 degrees is 1.732 plus 1 over times 37.5 degrees is 1.3032. So in conclusion, we found out that 2 equals to R times 1.732 plus 1.3032. That is actually equals to 3.0352. So in conclusion, we found out that 2 equals to R times 3.0352. We divided this equation by 3.0352 and finally found out that R, the radius of the circle, the radius that we are looking for, equals to 2 over 3.0352. That is actually 0.6589. So in both methods, we found out that the radius R of this circle equals to 0.6589 units. Okay, thank you very much.